Alright, so last time we ended with talking about exponential functions, which were functions that curve up extremely fast. Well, this is the inverse of an exponential function. It's a log function. Log functions curve upward, but extremely slow. They go up as slow as a logarithm does fast. Okay, they're very, very slow. And they are what we call inverses. So another example of inverse functions are squaring and square rooting, okay? Multiplying, dividing, cubing, cube root. Well, exponentials and logs are also inverses of each other. Okay, so there's a test called the vertical line test, and what does that test tell you? Yeah.
If it's like an actual, like, if the equation is real or not.
So the key word we got to mention. It does tell you something about a graph, though, yeah? If it's a function. So if something passes the vertical line test, it tells you that is a function. Now, I don't know if you've ever talked about the horizontal line test. That is another test. So it might not be a recall, it might be new for some people. But what the horizontal line test tells you is if the inverse of your graph is a function. So a vertical line test tells you if the graph itself is a function. The horizontal line test tells you if the inverse of your graph is a function. So when we study like sine and cosine waves, that's a sine wave, and it fails the horizontal line test. Failing the test means it horizontal line hits it more than once. So because this graph fails the horizontal line test, its inverse would not be a function. So if the regular graph fails the horizontal line test, then the inverse of that graph would fail the vertical line test. All right, let's think about what an exponential function looks like. That's an exponential function. Okay, here's a horizontal line. Does an exponential function pass the horizontal line test?
Yes.
Yes. No matter where I put a horizontal line, it's only going to hit once. Okay, so think about what that means. The exponential functions pass the horizontal line test. So what does that mean?
So would that mean a logarithmic function would pass the test?
Vertical line test? Exactly. So log functions are the inverse of exponentials, and exponentials pass the horizontal line test. So that means logarithms pass the vertical line test, which means logarithms are
a function.
Functions. Exactly. Perfect. So when we draw logarithms, they are functions. They pass the vertical line test. The calculator does not do a really good job of drawing logarithms. So I'm going to show you what it does, and then I'm going to show you what it should look like. Part of a logarithm gets really steep. We learned that when the calculator has to draw something steep, it just doesn't do it right. So visually, what it means for things to be inverses of each other, they are mirror images over the line y equals x. So I'm going to draw an exponential, and then I'm going to draw a log, and then I'll draw the line y equals x. And you'll see that they are mirror images. Okay, so in blue, that's the exponential. In black, that's the line y equals x. And in red, well, that is a log function, but it's not drawn right. So the log function should look like this. It just keeps going down. Okay, so exponential, log, and if you could fold that right on the black line, the blue graph would land on top of the red graph. So logarithms and exponentials are mirror images over that diagonal line. And that's true for any inverse functions. If you graph a square root and a square function, their mirror images, they look a little different than that, but they are mirror images.
So, could you say that a y equals x line could indicate if a graph is inverse?
Yes, if you have two pictures and you could fold them right on that line and they land on top of each other, then they are inverses. Yep. We don't do a lot with like pretending like we're folding it, but it's just a visual so you can kind of think about what it looks like. Now, let's think about the exponential function. What kind of asymptote does the blue graph have?
A vertical asymptote.
So think about like exponential functions. When if you've got something like this, as x gets more and more negative, you end up with a really big number in the denominator. So what does y approach as x gets more and more negative? Yeah?
0.
Yeah, it approaches 0. And what kind of asymptote is it if y equals 0?
Horizontal.
It's a horizontal. Yeah. So we've got a horizontal asymptote for the blue graph right there. Now, exponential functions have horizontal asymptotes. What kind of asymptotes do you think logs have? They have vertical. Everything is switched between exponential and logs. So log functions have vertical asymptotes. And when we sketch logs, that's going to be the first thing we find. Because once you know where your asymptote is, then all you have to do is either sketch it that way or that way. Depends if you reflect it or not. A standard log function always curves to the right. Now, if you reflect it, it could curve to the left. Okay? But if you don't reflect it, that's how it always works. Okay, so we'll talk a little bit about how you write logs. First of all, if this was lined paper, that's about what it would look like. Okay, there are no exponents in what I just wrote. The A is a subscript, okay, that would be below the line. The Y, the equals, the log, and the X, those are all right on the line. If you had an exponent, it would be up there like that. Okay. And the way that you read that is y equals, and then you just read left to right. Log base A of x. That's how you pronounce it. Y equals log base A of x. And what that base does is it changes the kind of logarithm that you're taking. Just like if you do this. If you change that number, it changes the kind of root that you're taking. This is a cube root. That's a fourth root. Well, that's a log with a base of 5. That's a log with a base of 7. It's similar to cube root and fourth root. It's still a log. It's just a different type of log, just like those are different types of roots. Now this, okay, that's the thing that you're taking the log of. That's called the argument. When we deal with radicals, we call it the radicand. It's the thing that you're like square rooting. In a log, they just call it the argument. Right? So if I wrote, say, log base 2 of 15. 2 is the base, and 15 is the argument. So I'm taking the log of 15, and the type of log that I'm going to do is a base 2 log. So any question on how to write it or pronounce it?
Can you say the one you just wrote again?
This one is log base 2 of 15. So you're taking the log of 15, and the type of log is a base 2 logarithm. Base 2, that's not a very common logarithm to do. There are 2 that are pretty common, and we'll talk about what those are called. There's one of them. So if the base is a 10, that's called a common log. And because base 10 is used so much, a lot of times when it is a base 10, they don't even write the base. It's the only logarithm that, when you write the word log, L-O-G, if you don't put a base, it's always assumed to be a 10. So if you wrote this, even though there's no base there, it's assumed to be a 10. It'd be the same as this. You'll never see it the way that's on the right, though. And it is one of two logs that you can do on the calculator. So if you look on the left-hand side, right next to the 7, there's a button that says log. And you can press it. And when you do it, you can put in a number. Notice there's no base here. It just says log of 13. The base is assumed to be 10. I'll talk more about what is that 1.1139. Like, well, what is that? Well, it means something. I'll show you what it means in a minute. Okay. Any question on what a common log is? It's a base 10. Yeah.
Is it possible to do log base anything on the calculator?
Any base that's a positive number.
No, as in to input that into the calculator.
Yes.
Well, I can't because it's locked behind test mode.
We'll talk about how you put it in. Maybe if not tomorrow, next
You're
academic.
trying to go what log base?
Yeah, log base.
Oh, you click map and scroll down.
Yeah, it might not work on those calculators.
Yeah,
Online.
test mode enabled, meaning it doesn't work for that
Yeah.
one and
yeah,
the other one right above.
I have a sister, so.
I'll show you how to do it.
Alright.
So let me go back to that one for a second. Where's that number I typed in? So the log of 13 is 1.1139. Well, first thing to make sure you kind of understand about logarithms is that logarithms are exponents. Whenever you press the word log and you hit enter, the answer that you get is an exponent. But an exponent on what? On the base. What did we say the base of this log is?
10.
10. Watch what happens if you take 10 and raise it to the 11394 power. Anybody have a guess what you're going to get?
13.
Yeah, you're going to get about 13. So you just solved for what power would you raise the base to get the argument. That's what a logarithm is.
What would that look like if we were to put it like in a format? Like the way you put like log A of, or log A in X. How would that look like?
How would this look?
Yeah, like how would you like flip it?
Well,
So like let's say you have log A X. How would
log
you-
base A of X.
How
yeah.
would it look like in that form?
In that form, it would look like this. Log base 10 of 13.
No, like how do you put in that? Like let's say if you were to plug in everything, how would log AX look if it was like that?
I think I'll probably answer your question in a minute. We're going to talk about how you can change
Yeah, that's what I was
between log form and exponential form. And I think that'll answer your question. So we know logs and exponentials are inverses of each other. Well, there's a way to take a log equation and change it to an exponential, and take an exponential and change it to a log. And I'm going to show you. So one other special logarithm you can have is E, and that's a base. Did we talk about E
Yeah.
quickly before?
We thought about the fraction and then I take a special number and we had it in notes. We
Yeah.
discussed it afterward.
So 2.718. We talked about that
We talked about it like a little bit.
a little bit. So E is another number in math. It's like pi. It's a special constant. And if you have a log and the base is an E, that's called a natural log. Those are the only two logarithms that have special names. Base 10 is a common log, base e is a natural log. Anything else is just log base 5, log base 6. There's no special name.
Where does E come from?
E? So E is named after someone. It's called Euler's constant, and he's German, so his name is spelled, as you might think when I say Euler, it's O. In German, the U is an Oi sound.
Yeah.
So this guy's name is Euler, and that constant is named after him.
Because like pi comes from like it's all like circles. Like
Yeah.
that is-
I don't know why they use the Greek letter pi for 3.14,
Yeah.
but I know they use the English letter E because this is the guy that figured out it was 2.718.
But like what? What equals 2 point? But where is the E? Like what did he do with the numbers to get?
Oh, what did he do to calculate E?
Yeah.
I don't know off the top of my head how it is calculated. I do know that if you take, if you graph that in y1, it has a horizontal asymptote at exactly 2.718. So this special function has a horizontal asymptote at 1 point at E. But yeah, I'm not exactly sure how you derive E.
Yeah.
I mean, I know how you derive pi. You take, circumference equals pi times diameter. You take the diameter of a circle, or you take the circumference of the circle, you divide by its diameter, and that gives you 3.14. Yeah, so look up how do you calculate E. Now, because log base E is another log that's used a lot, they normally don't write log base E. So it's only 4 letters, but they shorten it to 2 letters. And the 2-letter abbreviation for log base E is lowercase l, lowercase m. And that's important to know because your calculator has a button that says LM. It's the button right below the log on the left-hand side. It's closer to the number 4. The thing you have to remember about ln is that if I ask you what's the base there, you don't see a base. There is no letter that's written lower. But the base is an E. It's like it's hidden, okay, in the abbreviation. Right, so instead of writing something like this, let's say you wanted to take the logarithm of 14 and you want to do a base E logarithm. You'd never see it like that. You'd see that. And again, kind of another weird thing, it's a natural logarithm. So why isn't it NL instead of LM? I don't know. Natural logarithm.
Is that the IN of X or is the LN of X?
LM.
Okay.
LM.
Does that stand for anything? Is it just LN?
What does LN stand for?
Natural logarithm.
Natural logarithm.
Oh.
Natural logarithm. Yep. And there is, again, the button for it. As I just said, it's right here. So if you want to know the ln of 14, it's 2.639. So what's the base that's hidden in the ln? E. So if you take E and you raise it to the 2.639 power, you should get about what number?
14.
14. That's the exponent that you would raise the base to get 14. And you could try it. It'll be about 14. Right, but that's an important idea. Okay, logarithms are exponents. That's what they are. Okay, let's go back to the picture for a second of the log. So look at the graph in red. Does it look like the graph in red goes left and right forever? No, it stops. In this case, where does it stop? On the left side. Yeah.
It stops about at 0.
And does it reach 0?
No.
No, because that's an asymptote. So it goes to 0, and then how far right does it go?
Mirage.
Infinite, yeah. So the domain of a logarithm function is 0 to infinity. You cannot plug negative numbers into a log. If you do, but you can. But you'll get imaginary, and we're not doing imaginary logs. How about the range? How far down does the graph in red go?
Negative.
And how far up?
Positive infinity.
Yep. The range of a logarithm is all real numbers. Now, you can't do anything to change the range. If you shift it up and down, you stretch it up and down, it doesn't change. But you can change the domain. Like if you shift it right 2 units, well, then the domain would be 2 to infinity. But the important thing about a log is you cannot take the log of a negative number and get a real answer. Okay, so now I'm going to talk a little bit more about the question that was kind of asked. How do you change between log form and exponential form? And to convert between the two, there's no real math involved. It's more of just rearranging where things are. Okay, so on the left, that's log form. Y equals log base A of x. So there's 3 things there. There's a y, there's an a, and there's an x. When we rewrite it in what's called exponential form, it's going to look like this. That's exponential form. There's no word log. There's a base, there's an exponent, and then there's something on the other side. So when we rewrite it in exponential form, that's how it looks. All right, let's just see if we can kind of figure out what letters go where and maybe how that makes sense. Let's start with the A. What's the A called on the log? It's the base. When you rewrite it as an exponential, it's still the base. It's the thing that's lower. So the base on the log becomes the base on the exponential. Right? Now, I've said it a few times. Logarithms always equal what kind of number? Exponents. It's very important. Logarithm, whenever you calculate a logarithm, you are finding an exponent. That's why y is the exponent. It tells you what power can you raise the base to get this. And does anybody remember what that's called?
The argument.
The argument. And the way you can remember it's the argument is if you argue with somebody, eventually you end up by yourself on the other side. You end up alone. So the argument ends up alone on the other side. Okay, so argument, base, exponent. Argument, base, exponent. And that's it. That's how you change between log form and exponential form. So let's try a few examples. Okay, that is log form. Okay, so we're going to change to exponential. Right, let's start with our base. Okay, what's the base there? Base is 3. Logarithms always equal what kind of number?
Exponents.
Exponent. So y becomes the exponent.
What is that?
And the argument ends up by itself on the other side. Now that one we can't do anything with because we don't know y. If we knew y was 2, well then we could do 3 squared and write the answer. That's all you can do. Let's try this one. So here's another equation in log form. What would it be in exponential form? Yep. Okay.
5 to the power of y equals x.
Base, logarithm equals the exponent. There's your argument. Any question on changing from log to exponential? Again, nothing you can do with that because you don't know what y is. But if you did, then you could solve for x. Let's try the other one. So now that's exponential. I want to make it log. If you want to make it log form, what do you think the first thing you have to write down is? Yeah.
3 equals.
You are going to put that, but even before you put that, there's something you got to put. This really tells you that it's log. Yeah? Log. Yeah, I usually just put the word log. But then, as you said, that's going to be the exponent. So the logarithm equals the exponent. What was the base on my exponential? 1.2. So that becomes the base on my log. And what do we call the thing that was by itself? The argument. So you're taking the log of m, and the type of log is a base 1.2. And that's it. Yes?
I know what would be.
You know what m would be?
Yeah.
Yeah.
Since we have 2 of the numbers already, we can figure it out.
Right, we could figure it out. Yeah.
It'll be 1.728.
You don't have to find m in this case, but they might ask you to sometime. Yeah. Let's try this one. E to the b equals 9. So Ryan, what's the first thing I'm going to write down if I'm going to change this to log form? Yep, let's put the word log. And what's this log going to equal? Yeah, b. Logarithm always equals the exponent. What's going to be the base on my log? Yeah? E. We'll come back to that, but that's, yeah, log base e for now. And what's my argument? 9. Now, log base e, we want to abbreviate that. What did we say the abbreviation is? Yeah? ln. And that's something you could type in on the calculator, the natural log of 9. Question on that? All right, let's try this. So a little different, but it says to show that log base 2 of 8 equals 3. Well, what type of equation is that? Is that a log equation or exponential? That's a log. What's the only thing that I've shown you how to do so far with a log equation?
We'll change it to exponential.
Change it to exponential. So let's change it and see what happens. What's my base? 2. Rich, what's my exponent here? 3. Logarithm always equals the exponent. And what ends up by itself on the other side? How about Mike? Yeah, the 8. So does 2 cubed equal 8?
Yes.
Yeah. So we just showed that log base 2 of 8 equals 3. This is basically saying 2 to the 3rd power would give you the argument. That's a logarithm. Let's try this one. Now this time it's not saying to show or to prove. They're not telling you what the answer is. You have to figure it out. Okay. Mia, what kind of equation is that? Log or exponential? That's a log. Yep. And Veronica, what's my base there?
5.
Yep, 5 is my base. Aiden, what's my exponent?
1/25. No, x.
X. So logarithm always equals the exponent, so 5 to the x. And Lily, what's going to go on the other side? 1 to 25. So now it's just a matter of 5 to what power gives you 1 over 25, not 25. Yeah?
Well, it's going to be -2.
Yep.
Because when you're dealing with a negative exponent, you'll flip it, so it'd be 1 over 5 to the power of 2.
Right.
Which would then be 5.
So the answer there, yep, -2. Now, if that fraction was 1 over 24 instead of 1 over 25, well, now we got a little bit of a problem. So we're not going to talk about that yet. Any question on that? Okay. All right, let's try this one. So it's a log equation, and the variable is in the argument. Jacob, what could I do with this one?
We can turn into an exponential.
Yeah, and what would it be if you rewrite it as an exponential?
5 to the 1.5%.
Exactly. And you're done. You could do 5 to the 1.5 power. If the power starts to get too big, we wouldn't do it out. If it was 5 to the 30th power, we just leave it. But that's small enough, you could do it out. Any question on that? Okay, so the variable was in the argument. Let's try one where the variable is in the base. Gabby, what would that one look like if we rewrite it in exponential form? So, what's your base? Start with that. So x is your base. And logarithms always equal what kind of number? The exponent. Yeah. Logarithms always equal the exponent. And do you remember what the thing is that we call that always ends up alone? The argument. Right. And now we just have to solve that for x. Rory, how do I solve that?
You would square root it.
Okay, and when you square root it, you get that. Now, should I do positive or negative root, or just the positive? Yeah, just the positive, because remember what we said about the domain. Technically, we only talked about the argument being greater than 0, but the same rule applies for the base. Both the base and the argument have to be numbers bigger than 0. So negative square root of 3, even though it would be a solution to this equation, it's not a solution to the log problem because it's not in the domain. Any question on that? So let's look at a couple special properties. We're going to look at four different properties. And these properties are more like a special pattern, where if you see this pattern, the answer is automatically going to be a certain number. Here's our first pattern. Now, just focusing on the red boxes, is this a log equation or exponential? What format? Yeah.
This looks more like an exponential.
That is an exponential. You have a base, you have a power, and you have something on the other side. To be a log equation, it has to have the word log, but not in an exponent. Okay, so that's exponential. And what happens is, if you had something like 3 to the log base 3 of 12, if this number and that number match, then something special happens. If they match, then they cancel out. And the answer that you're left with is whatever number was sitting right here. So it's a special pattern. So in my case, 3 to the log base 3 of 12, what do you think that would equal? 12. Yeah. It would equal 12. Now, let's look at that one and see why is that true? What kind of equation did we just say it was? Log or exponential?
Exponential.
That's exponential. So then let's change it to log form and see what happens. Okay, so we're going to change it to log form. What's the first thing you write down? Log. So put the word log. What's going to be the base on my logarithm? Does it come from box 1, box 2, or box 3?
Box 1
Box
is going
1.
to be the base.
Yep. box 1 is your base, so that's going to be my base.
So it'll equal out to being the exact same thing of log a x is equal to log a x.
So yeah, what does a logarithm always equal? It always equals the exponent, which is box 2, log base a of x. And the only box I haven't used is what? Box 3, right? That was all by itself on the other side, and what was by itself becomes the what? The argument. So all that this rule is really saying is that something is always equal to itself. It's basically the reflexive property. Log base a of x equals log base a of x, of course. Something is always equal to itself. Let's try this one. Similar to rule 1, it's another property where if the base on your log and the base on your exponential expression and the argument match, then the answer is whatever your exponent was. Now, does that one look more like a log equation or exponential?
A logarithm.
That's log. You've got something here, here, and here. Doesn't matter what's in those three things, but if it looks like that format, that's log. Well, let's change it to exponential and watch what happens. Just so we know what box we're talking about. What's your base here? What box is that from? Yeah, your base is A. Logarithm always equals what kind of number?
The
Exponent. So box 3 is an exponent. And what ends up
The argument.
by itself on the other side? The argument, which is box 2. Again, it's the reflexive property. It's just another way of saying something is always equal to itself. You've probably never seen the property like that before, but that's how you write the property as a logarithm. Let's look at this one. Log base A of A. So this is a property where the base on the log matches the argument. And it's always 1. Well, let's change it to exponential, and you'll see that this is a rule from Algebra 1. Let's call that box 1, 2, and 3. All right, what's your base here? What box? Yeah, box 1 is your base. What box is your exponent? Yeah, box 3. And the only thing we haven't used yet is the argument, and it ends up by itself on the other side. What is that saying, really? What I just circled? It's saying, yeah? Yeah. Property 3 is just saying that anything to the power of 1 gives you the same answer back. This is how you probably see it in Algebra 1. This is how you can say the same rule as a logarithm. All right. And let's look at this one. If you take the log of 1, the answer is always 0. Doesn't matter what the base is. Any base. Well, let's see why that one is true. So the property is what's on the left. That's the important part. On the right is the reason why. Anyone think they can tell me why the logarithm of 1 is always 0? Yeah?
Anything to the power of 0.
Exactly. Anything to the 0 power is 1. A to the 0 equals 1. So those are just a few kind of simple properties that when they pop up with logs, we can simplify it quickly. So let me keep those up, and we'll try a few examples. Now, we're not going to go through the reason why every time we do a problem. We're just going to use the property. So the first one, which property does that one look like? Out of properties 1 through 4. It is. It's property 1. Okay, we're going to put the answer right there. So it's property 1 where A is 2 and X is pi. So what would be the answer when you simplify that one? Yeah.
Pi.
Pi. Yep. The answer is pi. Let's try this one. Which property does that one look like?
2.
That is property 2. And using that property, what would it simplify to?
-4.
-4. All right, let's look at this one. A little bit harder, but it is still one of the properties. Anyone think they see which property that one is?
I'm pretty sure that would be 2.
Yep.
Again,
Could we make it a little clearer
it would,
to say that?
for the way it would be shown is log base of e
Yes.
with the other thing e to the power of kt.
Yep.
And it would be equal to just kt.
Whatever k times t is. So that ln hides the base, so it might be a little confusing when you look at it, but if you write ln the long way, you can see that it's rule property 2. I don't think I had one for property 3 or 4. Let's make one up. D. How about log base 3 of 1? Yeah. It's going to be what? Property 1. Well, property 1 would have to be exponential form. This is log
Pretty
form.
sure she said property 4.
Oh, did you say 4? I can't hear you clearly. I'm sorry. So yeah, it is property 4. And what's the answer?
0.
Doesn't matter what the base is. Anytime you take the log of 1, the answer is always 0. Any question on that? Those are just some special properties. Okay, last thing. So the last thing we're going to look at for today is properties we can use to take a logarithm that's together and split it apart, or take a logarithm that's already been split apart and put it back together. It's the same properties, just depends which way you use it. Okay. So here's our first property. If you take the logarithm of a product, you can split that apart as a sum. In fact, you can split it into as many sums as you have factors. So if you had x times y times z inside, it'd be log x plus log y plus log z. So a product changes to a sum. Whatever the base was to start the problem, that's the base that remains through the whole thing, whether you're splitting it or combining it.
Similar. I was gonna ask, like, I can't remember if it would be possible to type a specific base for log in the calculator.
So the only thing I've shown you so far is how to type in 2 bases. I showed you guys how to type in base. What's one base? Yeah, 10.
The common and then the natural.
And the natural, which is base E. As for anything else, I'll show you in the future.
One of our calculators can actually do it.
So here's an example. If you had the log of 4 times 5, it would be exactly the same as taking log 4 plus log 5. If you put your parentheses.
Yeah.
So that's an important thing. You need to close your parentheses or it doesn't come out. Okay. Same thing. Based on that, anyone think they could give me another way that I could get the same answer instead of log 4 plus log 5?
Could you do the log a of 20?
Yeah, so I could do log 20. How about something with a plus sign between them? Yeah.
Log 10 plus log 2.
Log 10 plus log 2. Yeah. Log 40 plus log of 1/2. No. Any 2 numbers that multiply to give you 20 would give you the same answer. Now, that's a product. Product turns into a sum. What do you think a quotient turns into?
Subtraction.
Subtraction. Yep. So if you're dividing two logs, you can turn it into a subtraction problem. The order is important. It has to be the log of the numerator minus the log of the denominator. And again, the base can be any base you want. Just whatever the base starts as, keep it the same. Even if it's base E. If it's base E, you'd see the same property with LNs. So it works there too. And I'm not going to take that one in, but you could. And you'll see what you get. It works.
So I found out how to calculate E.
Oh, you did?
Yeah.
Can you tell me after?
Yeah.
All right. Let me know after, because I am interested. Is it a repeated fraction?
No,
Oh.
it's a function.
Oh, okay.
It's kind of what you wrote.
Oh. So, the last property I want to look at is this one. Let's say we had log of m cubed. Well, when we're dealing with logs, we don't want to have exponents on arguments. It's going to make things complicated. So there is a way we can get rid of this 3, though. What does m cubed mean? If I write that out the long way, yeah? Okay, even before we jump to that step, which is exactly where I'm going to jump to, what does just m cubed mean? Yeah? It means m times m times m. And right, we can change that to addition. It's log m plus another log m plus another log m. So what's log m added up that many times? 3 log m. So the rule, when you have an exponent on an argument in a log, you are allowed to take the exponent and put it in front. And that's what I'm saying in this property. Exponents can go in front. What that's called is writing the exponent as a factor, because you've changed it to multiplication in front of the log. Okay, so that's called expressing the exponent as a factor. Instead of having 3 to the 5th power, now you have 5 times something. So you made the 5 a factor. Now, when we do problems, sometime it's going to tell you in the directions, express powers as factors. That means do exactly what we did in Rule 3. Put the powers in front. I said express powers as factors. And you left, excuse me, you left this as a final answer. That would be wrong. You might look at it and say, well, there are no powers there. But we talked about this. There is a power there. Yeah. It's really to the 1/2, right? This is that. So if you leave square root, you've left a 1/2 exponent hidden in the problem. And where should the 1/2 go?
In front of the log.
It should go in front. So if they say to express powers as factors and you have a root, that's what you need to do. Okay? That's what we just said.
What happened if you had a factor also like a root or something? So like for example, you had 1/2 and then you added x to a half. How would you?
1/2 log
And the next half. How would you?
x to the half.
Yeah.
Well, when it goes in front, it's going to be the product. So it's going to be 1/4 log x. Yeah, so you can combine them like that. That does work. Yeah.
For the 5.4 unit, are we going to have to worry about putting stuff presented to us being put to like a negative power and us having to solve like fractional log stuff? Like, because if something is to like the negative something power, we have to like put it into a fraction to like show it's like form. So are we gonna need to worry about that for logs?
Yes, you could have negative powers like we did in this problem. So that was the answer here was a -2. Yes.
What if there was already a factor in front of the log, and then in the argument there was also an exponent? Is that?
Can you explain that?
Did you just say that?
Yeah.
I just missed that.
So when we had, like if you had a 1/2 in front and then you have a half here,
Yeah.
you can, when you put the 1/2 in front, it becomes half of a half or a
So
quarter.
is it like multiplying?
Okay, any question on that? But yeah, that could happen. So that's important. All right, let's try this. So it says to separate it into multiple logs. If you end up with exponents, put them in front. That's what that last sentence is saying. Okay. So inside the parentheses, do we have a product or a quotient? Yep, product. And how does a product split? Is it a sum or difference? It's a sum. So we're going to have 2 logs. What is going to be the base on each log? It's going to stay exactly the same as the original. And my first argument, my first factor, and my second argument, second factor. That's it. That's how you separate that into 2 logs. Any question on that one? All right. Let's try this one. Log base 2 of 5 times r cubed. Okay. What's going on inside the parentheses there? Is it a product or a quotient? Yeah? It's a product. So it's, again, it's going to be 2 logs. And because it's a product, is that a sum or difference? That's a sum. My base on each log? 2. Okay, first argument, 5, that's okay. Now, what would the second argument be just in the first state? The second argument is what? R cubed.
Oh, but you can put the 3 in front.
But we have to put the 3 in the front. So it's 3 log base 2 of r. Okay, any question on that? If you don't put the 3 in front, you haven't done the last sentence. Express powers as factors.
That 3 wouldn't apply to the first one, the log of 5.
No, because the 5 isn't being cubed, just the r. Now, if you had this,
If the cube was outside of the parentheses,
That's-
it
yeah,
would-
that's-
since
that's-
it's inside, it isn't.
totally different. Now you're going to cube the 5 and the r. Yeah, exactly. Okay, how about this one? Product or quotient? Quotient. So when we split this one up, how is it going to split? Since it's a quotient.
They're basically 9, and then
Yeah.
also be subtracted.
It's going to be subtracted. Okay, my first argument has to be the one in the top, and the second argument, 2, the one in the bottom. There you go. All right, and let's try this one. Now, this is just log base e. You don't write it log base e. You write your final answer with ln. So, anyone think they could tell me the final answer in one step? Yep.
It would be 3 ln y. Minus ln e.
Perfect. There you go. 3 ln y minus ln. Questions on it? Let's try one more splitting and then we'll do the reverse, combining. But if you can split, you can combine. It's the same steps, just backwards. Let's try this one. Okay, what's going on inside the parentheses? Product or quotient? Overall. Look at the kind of the big picture. That's a quotient. So quotient turns into,
The quotient would be subtraction.
subtraction.
We'd have ln on both sides. we'd have 2 ln x on the left side. We'd have 3 ln x minus 1 in parentheses on the other side.
Yeah, and you do want to put that in parentheses because there's a difference between the ln of x minus 1 and the ln of x minus 1. If you leave it kind of vague to somebody, well, do you mean the x minus 1 is part of the argument or is it not? And the difference is either a horizontal shift or a vertical shift. That's a shift down one. That's a shift right one. So they are different. And we'll talk about the differences of transformations tomorrow. Okay. So let's take a look at recombining back as a single log. So now it says combine into a single log, express factors as powers. That means take exponents and put them back up. Okay. So what do you think the first thing you would do here is, and it would be the last thing you would have done to get this answer, except reversed? Yeah? Put the 4 back as an exponent on the 3. All right. And now that's a calculation. We can do that out. What's 3 to the 4th power? Yeah.
81.
81.
Next, so if we recombine everything back together to be log a
So
7 times 81, which would then go log a 567.
Yep. So that's exactly the process we just did, except reversed. Now, a lot of times in the homework, they might say, like off to the side, where a is greater than 0. They're just saying that so you know you're not dealing with imaginary logs. It doesn't change how you do anything. It's just if a wasn't greater than 0, then you'd have imaginaries. So if you see that on the side of the homework, don't let it trick you or mess you up. All right, let's try this one. Let me fix that. Okay. What's the first thing I could do with my first logarithm? Yeah. Yep, 8 to the 2/3. Now, do people know how to do a fractional exponent in your head? If it's going to come out to a nice answer? So, the way you do it is that I wrote 2/3 horizontally on purpose, because I think it makes it easier to see what to do. First thing you do is that.
16.
What's 8 squared?
64.
64. And dividing by 3 is what kind of root?
Cube.
It's a cube root. So this means take 64 and find the cube root. So what's the cube root of 64? 4. Now, if it didn't come out to a nice answer, then you can't do it in your head. You gotta use a calculator. Right? So that's the ln of 4 minus, well, what was 3 to the 4th? We just did that.
81.
81 minus 71. 10. So that's ln 4 minus ln 10. Try to make your 1s and your lowercase l's look different, otherwise you're going to get messed up. And what does that turn into when we combine it back together? Yeah.
It would be ln 4 over 10, and if you want to simplify it more, it would be ln 0.4.
Yeah, you could do 0.4, you could leave it as 2/5. Either way.
Where'd you get the ln of 10 from?
So that was 3 to the 4th minus 71.
We have 81.
81 minus 71.
Oh, okay. Yep.
Any question on that one? That's combining and splitting logs. So 3 things we really looked at: how to change between log and exponential, how to use those 4 special properties, and how to combine and split logarithms. And that's really it for 5.4 part 1. 5.4 part 2 probably take us about 30 minutes, 35 minutes tomorrow maybe. So we can go over homework for like 40 minutes if we needed to, and I think we'd still have enough time to finish up. So that's the homework. 1 through 7, 13 to 17, 21 to 27, and 29 to 33. Yes.
I have a question for the homework.
Question on the homework?
Yeah.
Okay, let me just pause here.
Yeah.
Everybody, make sure you get that.
Oh, hold on.
Maybe